The optimization of espresso extraction is a problem of mass transfer physics. To achieve a perfect cup, we must look past barista intuition and rely entirely on fluid dynamics and empirical data. The primary metric for extraction efficiency is extraction yield, or EY. This number represents the fraction of solid coffee grounds that successfully dissolve into the liquid. It is calculated directly from two other measurements: the brew weight of the final beverage and the total dissolved solids, or TDS, contained within it. This is the Specialty Coffee Association's Coffee Brewing Control Chart. Notice the specific target box highlighted here. For decades, the industry standard for an optimal cup has been defined as landing strictly between an 18 to 22% extraction yield, with a TDS of 1.15 to 1.35%. Knowing the exact mathematical coordinates of a perfect extraction is different from reliably hitting them. Historically, the coffee industry has relied on variables like grind feeling by touch or manual tamping force, methods causing the actual extraction results to fluctuate wildly. Achieving perfect consistency requires isolating and controlling the physical vectors of mass transfer. We must bypass assumed best practices and look directly at the raw mechanics. We begin by eliminating mechanical confounders. A rigorous ANOVA study conducted by Socratic Coffee tested the impact of mechanical compression, or tamping, on a coffee bed. The researchers executed extractions under strictly controlled tamping pressures, scaling incrementally from 5 kilograms of downward force all the way up to 20 kilograms. This bar chart plots the resulting total dissolved solids output against those 4 tamping pressures. As the force increases from 5 to 20 kilograms, the trend line remains completely flat. There is zero statistical variance between the samples. Physical tamping force has zero statistically significant impact on the amount of coffee dissolved into the cup. The physical compression of the grounds does not dictate the extraction. Clearing this variable from the board leads us to a core paradox. The industry operates on the assumption that grinding coffee finer will always yield a higher extraction. Since mechanical compression is a false variable, extraction efficiency is actually governed entirely by fluid dynamics. Specifically, it depends on how the pressurized water interacts with the particle size distribution of the ground coffee. The mechanical process of grinding roasted coffee beans does not produce a uniform powder. The fracturing of the brittle beans generates a specific, uneven spread of particle sizes. This particle size distribution curve reveals two distinct peaks. The larger right peak represents boulders, particles over 100 micrometers, dictated by the Burr gap. The sharp left peak represents fines, particles under 100 micrometers, created as dust at the fracture interfaces when beans shatter. To model how water pulls soluble compounds from these particles, physicists use advection diffusion equations. This theoretical mass transfer model tracks the journey of solubles from the interior of the coffee particle out into the surrounding liquid. The governing mathematical assumption here is straightforward. Reducing the overall grind size decreases the diameter of the boulders. This exposes more surface area to the water and shortens the physical transport pathways the soluble compounds must travel to escape the particle. According to the math, extraction yield should increase monotonically. As the grind setting becomes finer, the extraction efficiency should reliably and continuously rise. That is the theoretical model. But when a team of mathematicians and chemists, led by Michael Cameron, tested this in a laboratory setting, the physical reality failed to match the math. Here, extraction yield is plotted against grind setting. The blue line shows the theoretical smooth increase. The red line shows empirical data. It tracks the theory initially, but around grind setting 1.7, it abruptly peaks and completely collapses, yielding significantly less dissolved coffee. Researchers define this failing zone on the right side of the graph as the partially clogged flow regime. The physical cause is a structural collapse of the coffee bed. At extremely fine settings, the sheer density of those sub-100 micrometer fines causes the particles to aggregate and clump together when exposed to pressurized water. Grinding finer past this critical threshold creates impenetrable microstructures that actively destroy extraction efficiency. The aggregation prevents water from accessing the internal surface area of the coffee bed. When pressurized water hits this highly restrictive, clumped environment, it desperately seeks the path of least resistance, tearing through whatever tiny fissures it can find. This schematic illustrates homogeneous flow. Water, the straight blue arrows, passes evenly through a neatly dispersed matrix of coffee particles. In the partially clogged flow regime, uniformity is destroyed. Particles clump together, and water fiercely channels through narrow gaps, completely bypassing the dense aggregates. Mathematical estimates show the severity of this inefficiency. During extreme channeling, up to 13.1% of the entire coffee bed can remain dry and completely untouched by the extraction process. This physical failure maps directly onto the chemical extraction rates of the solubles, which in turn defines the sensory reality in the cup. Localized areas subjected to the intense channeled water flow become severely overextracted. The high volume of water strips harsh, bitter compounds out of those specific particles. Simultaneously, the bypassed, dense pockets of coffee remain under-extracted. Because water barely penetrates them, they contribute highly acidic, sour compounds to the final liquid. A choked or overly fine espresso shot tastes simultaneously bitter and sour because of this severe inhomogeneous fluid dynamic failure. You are drinking a mixture of two distinct, flawed extractions. This leaves us with a strict engineering problem. We need to maximize extraction yield and guarantee cup-to-cup reproducibility while completely avoiding the partially clogged flow regime. The largest roadblock to solving this problem is a deeply entrenched industry rule. The Specialty Coffee Association has historically mandated that an espresso must take between 20 and 30 seconds to extract. Adhering to this arbitrary time target forces operators to manipulate the flow rate. To slow the water down enough to hit that 30-second mark, baristas grind the coffee finer, pushing the physical system directly into the inefficient, partially clogged flow regime. Respecting the actual physics of mass transfer requires discarding the clock entirely. Time cannot be the target variable. In a purely empirical system, extraction time is an output to be observed. It is not an input to be controlled. The optimal mathematical strategy to guarantee homogeneous flow begins with the mass of the coffee itself. By systematically reducing the dry mass of the coffee dose, we change the geometry of the resistance. Dropping the dose, for instance from 20 grams down to 15 grams, and combining that with a significantly coarser grind setting shifts the fluid dynamics. This diagram compares the two cross-sections. The left shows the traditional deep bed of fine particles with chaotic flow. The right shows a shallower bed of coarse particles with uniform extraction. The coarser grind prevents clumping, while the shallower depth reduces flow resistance. The operational outcome of this optimization is stark. With less resistance, the pressurized water passes through the granular bed rapidly, resulting in shot times as short as 14 seconds. Despite this rapid extraction time, the empirical data proves that the total dissolved mass in the cup is higher. The extraction is uniform, balanced, and highly reproducible shot after shot. There is also a secondary economic benefit. Implementing this mass transfer protocol results in a 25% reduction in dry coffee waste per beverage. Mastery of the cup is achieved through the management of fluid dynamics and mass transfer physics. Abandoning arbitrary traditions in favor of these physical constants ensures a level of precision that ensures both quality and efficiency.